then we can just go live. Sebastian is ready for you. I'll be doing a short introduction as always. So I'm just trying to admit everyone in this session. So just stand by, folks. Cool. We can go live in the next 30 seconds. Just trying to admit everyone to this call. Can see pretty more people trying to join in the call. So just stand by, everyone. Hello, Saeed. Hello, Jason. Alrighty. I think we are good to kick off from here. Cool. So, hey everyone, and welcome to Superhack workshop titled OP Stack Deep Dive. Joining us today is Sebastian, who will be taking us through this session. And with that, I'll pass it over to Sebastian to get the workshop started. Over to you, Sebastian.
Hey, yeah, thank you. Hello, everyone. Thanks for having me here. I'm a protocol engineer at OP Labs, and yeah, I will just show you a bit of what the OP stack can do and how you can hack it and how you can use it to test your hacks. So let's get ready with an architectural overview here. So as you know, OP Stack is a software to run a layer 2 chain, so a rollup chain. And in order to do that, we actually use the same split as L1 does between the so-called consensus layer, which is driven by the OP node in our case, and the execution layer, which is driven by OPGA in our case, at least in the reference implementation. But there are also other implementations of the execution layer, for example, OPRef. And you can actually also just use that one. Simply because I'm very familiar with the whole Go stack, I will use the Go stack as a reference in this workshop, but you can also use OPRef, for example. In general, the OP stack usually refers to the Go reference implementation, but yeah, you're totally open to also use other implementations. All right, so as you know, on L1, there's Go Ethereum, for example, as an execution client, and then there's also, for example, Lighthouse on the consensus layer to drive the network. And on layer 2, we have these pairs of OP nodes and OP gaps. So actually, the OP gaps are mostly not really connected to each other in an optimism network, but it's mostly the consensus layer OP nodes that are connected. The orange one here is a sequencer. So as you know right now, for example, on OP mainnet, we are running a central sequencer, and this sequencer basically ingests all the transactions that are coming in. Well, these are actually coming in via the execution layer. This is not really shown here. And then the sequencer is building the blocks, and then via gossip, and that is then gossip between the OP nodes, the new blocks are propagated. What is special about the OP stack here is that we have a separation of those concerns. So the sequencing is really just sequencing the so-called unsafe chain, right? That means, okay, it is just producing blocks at a rate of 2 seconds. But then what happens with those blocks, right? So they are propagated immediately, and then all the other chains are seeing the blocks. They're then sending them to the OPGAF node to then advance the chain, and then OPGAF will report back, okay, this has been a valid block, and this is how the chain progresses. But there's still no safety here, right? So what we really want to have is, for this to be a full rollup, is that there's actually some kind of connection between the layer 1 Ethereum and the layer 2 network. There's several things that are happening here in the background, but one very important component that actually makes this a rollup is then the OP batcher. So the OP batcher is continuously querying the sequencer for the latest unsafe chain. So unsafe is basically then, the tip of the chain that the sequencer is building. And then it is taking this unsafe chain and, you can call it rolling it up, basically taking several blocks together, compressing them, and then submitting them to the layer 1. And this is really what the batcher does. It queries continuously, it accumulates enough blocks, and then it sends them off to layer 1. as you all know, recently we have enabled blob support on layer 1, which is amazing. And this is also what the badger is using since then. So this is usually submitting 5 or 6 full blobs, and each blob has, around 130 kilobytes in size of data to the layer 1. And then that's where it is basically persisted, the whole chain data. So, but now what's happening now? So all the other nodes, you can also view them as validator nodes. They are watching the layer 1 and then continuously ingesting those rolled up blocks from layer 1, and then just checking that basically what the sequencer claimed via the unsafe blocks, what has been propagated, just to have like a very live network, is actually what is really being persisted on the layer 1. And if there was any error here, for example, it would actually cause a reorg, right? Because what is on layer 1 has higher authority than what is in the layer 2. What is basically propagated just by the sequencer. So this is basically how we get the so-called safe chain. And then the safe chain, just advances in steps, so to speak, because it always has a batch full of blocks. And then when the layer 1 block in which those blocks were contained finalized, right? So we have the concept of finalization on layer 1. Then actually we also call this the finalized chain on L2. So basically the chain that has been derived from finalized L1 data is then the finalized L2 chain. I will also later speak about how actually deposits work. So how do you get stuff like assets or any other messages from the layer 1 onto the layer 2? I will talk about that later. And then also talk about how do we actually get back onto the layer 1 from the layer 2. One important component to actually then get back is the so-called proposer. And what the proposer does is it regularly submits so-called output routes, which is kind of a state checkpoint of the layer 2 to L1, which means that when you want to claim a withdrawal layer on L1, you can actually reference that output route and then also provide like a Merkle proof that your withdrawal is actually included in that output route. And this is how you can then get out of the layer 2. Any questions so far about that? All right, so let's, if there were any questions, I didn't see it. Maybe I just don't understand how this works right now. Okay, so now this is, here I want to dig a bit deeper about how the layer.
Sorry.
Has it been?
Yeah. I actually had a quick question.
Yep.
I got confused when you said gossiping, or like whether, I don't know, execution or consensus or something. How is it relevant here if we only have like one sequencer? I thought that there's like no consensus actually. So what's gossiping really for?
So because we have this unsafe chain, which is advancing at a pace of a new block every 2 seconds, we also want to actually see, for example, if you go to Etherscan now, to optimistic Etherscan, you will actually see a new block every 2 seconds. And what Etherscan is showing you is not the data like derived from the layer 1, but is actually what it just received 2 seconds ago or 1 second ago from our sequencer. So basically our sequencer is just broadcasting out to the network on the OP node P2P network every new block, and then all the nodes amongst each other via gossip propagate these new blocks. And that's where the gossip is used here in that case.
Oh, okay. So it's like gossiping of the blocks then, right? Not like
it's gossiping new blocks. It's gossiping new blocks, and then there's other protocols in the gossip stack, in the P2P stack. For example, you can also, when you spin up your node and then you're missing a couple of blocks, you can also request missing blocks, like that are in the unsafe chain from other nodes. But basically, at some point, everything has to become safe via the layer 1. And this is then the, like consensus view that everyone has because it has landed on layer 1.
Oh, okay. Thank you. Thanks for clarifying.
Sure. All right. So now let's look at the deposit and withdrawal flow. So chains in the layer 2, right? We have on layer 1, we have a 12-second block time. And on the layer 2, we have a 2-second block time. But I'm just showing 3 blocks here because it would actually be a bit otherwise be a bit cramped. So we have always a sequence of blocks, of layer 2 blocks that all reference the same layer 1 block. This one is also called the L1 origin. And the first block in each sequence, the first L2 block in each sequence, always has a special row, because it is it always has to contain, that's by protocol, a so-called deposit transaction or deposited transaction. And this will contain any deposits that have been made on L1 into the layer 2. So there's a contract on layer 1, which is called the optimism portal. And you can send, for example, Ether or an ERC20 contract token to it. And then this will cause a deposit on layer 1. And then this will be ingested here on the layer 2 and then executed in this very first block. In addition, there's also some like special blocks that are deployed on layer 2. And then they also can, they're updated. For example, the information on gas of the layer 1. For example, in the layer 1 block would usually contain some, fields about the latest base fees. And then those base fees can also be accessed on the layer 2 by layer 2 contracts, like special contracts that are updated by the deposit transaction. And then all the other blocks are just pointing, at each other as normal in a blockchain, but they all reference the same L1 origin. The deposit also has a very important mechanism because it allows anyone to force, so to speak, a transaction on the layer 2 that is not, for example, if the sequencer were to, censor a transaction, then you could still force that this transaction is being used by depositing it, because, every other chain that is validating is also validating that the deposit transactions have found their way into the first block. So this is basically how you solve the censorship problem in this protocol. And then after a couple of L2 blocks, we have we have the L1 chain advancing, and then we have the next sequence of L2 blocks. And this is how they are tightly coupled, the L2 chain to the L1 chain. Okay, now you know how deposits work. And now you can also get back out of the network. So how you can do that is posting a so-called withdrawal transaction to the so-called L2 to L1 message passer. So this is a multi-step process actually to do withdrawals, which is a bit more complex. But what you do is basically send a withdrawal transaction, and then this transaction will actually be committed to in a later, if you remember, there was the proposer who was like continuously sending checkpoints to the L1. And then basically this checkpoint that the proposer posts is a commitment to the withdrawal that you were reserving here, so to speak, on the L2 to L1 message passer. And the optimism portal, which you used before to do a deposit, can then be queried to actually do a withdrawal proving. So this is then a process by which you send a proof that references the output route and your withdrawal. And then you can withdraw. The process is actually quite complex. It also has a challenge mechanism. Also, you may be aware that we recently launched fault proofs, and then with fault proofs, anyone can actually post those proposals, and then the proposals can be challenged. So yeah, it has gotten a bit more complex with fault proofs, how this mechanism to withdraw back out of the chain works. But this is high level how the deposit and withdrawal flow works, and also how the chain progression works. And yeah, you can see the connection basically between the layer 1 and layer 2. Okay, any questions to that? Because next I would actually dive into the so-called local DevNet, which is a nice environment that you can use locally to try out anything that you modify about the OP stack.
I have a quick question about the deposit part.
Yep.
So you say that when you call the deposit method on the L1 contract, then it can be read from the L2. So I was wondering, what's the technical mechanism by which they are reading the L1 state? Is it like part of the consensus, or like what's the mechanism technically that they read from the L1 contract?
Yeah, exactly. So it's part of the consensus that the sequencer has to take all the deposit contracts plus this special first deposit transaction that contains some metadata of the L1 and always transacts these deposits into the first block. So that is actually, it has to do that. Otherwise, the block it would be sequencing would be rejected by the network. So yeah, that's a consensus rule.
Got it. Thanks.
Yep.
Sorry, quick question here as well. Just
Yeah.
when you say deposits and withdrawals, just to be sure, are we talking like about some kind of bridging assets from the L1 to the L2, or is it does it have anything to do with the staking deposits? Just
Yeah,
to
this is really
understand the
about
context.
bridging. Yeah, this is bridging. So bridging
Okay.
Ether, bridging ERC20, bridging NFT. So all of that can be bridged via the portal. And that's why it has this nice name, portal. So you can send anything to the portal and then it will be available after, a few blocks on the L1. It's actually quite quick, the deposit.
It doesn't require for the contract, say I'm bridging an ERC20, say I'm bridging USDC. So I just deposit USDC on the L1 via the Optimism portal, and it will, the sequencer will know that I have USDC on the L2.
Yeah, so ERC20 and like many other assets have a somewhat like a setup process by which you actually need a pair of bridges, right? So you can have bridges that would then be built around the portal. So the portal provides like the raw protocol mechanism, but then around it you would have like a portal, like a bridge contract on L1 and also on L2, and that can be set up once. Then once the bridge is set up, you can then use this for transferring any assets back and forth. Yeah, actually, this is also something I wanted to quickly mention later and give a pointer at how you could actually build your own bridge as an example of a hack. Okay, so next up, just want to mention that OPGA is the reference execution layer client, and it has it's actually based on Go Ethereum, and one of the goals is that we try to keep the diff as minimal as possible, right? So this obviously has quite a few benefits because, well, if you have a small diff, it means that it's easier to maintain, and it also means that you have an equivalence to the layer 1 EVM. And this is what OPGA tries to achieve, and we also continuously update the software by merging in the latest upstream changes. So it really is kind of a fork of Go Ethereum. And just wanted to show you one thing here. So we have a very nice website that I also reference in the later, OPGA, and this is showing you the diff. So it's a very nice diff browser if you want to, because it has like sections and subsections of the core modifications, state transition, deposit transaction. I just talked about this. And they can actually click on each file that has a diff and then understand what has been changed. So for example, here we actually define the deposit transaction type as one of the transactions. And then, yeah, you can see how this is actually then being implemented with a transaction type. Yep, that's OPGA. And now we want to run our local DevNet. So how you do this is actually quite simple. And it's also a great starting point for development. So you just clone the monorepo, right? This is the monorepo. It's also later referenced. You just need to start a local Docker engine, and then you run make devnet up, and that's it. And we will actually do that right now. So here, I just did that before. So we will run make devnet up. It will be a bit quicker now for me than for you because it already in the background installs some dependencies. What it first does is it sets up the whole contract system. It generates the L1 and L2 Genesis blocks. It then builds a bunch of Docker containers and then deploys them all to the local Docker engine. And yeah, it actually just takes a few seconds once it has downloaded all the dependencies. And now we'll quickly go into the individual containers. Okay, it's done already. So here's my Docker engine. And as you can see, and you will actually see quite a few things that you saw in the overview here. So first of all, there's the L1, right? And the layer 1 that is running here now in Docker is actually a fully fledged layer 1 with a Lighthouse beacon node and verifier client, and then also an L1 Geth node. So here you can see, for example, in the logs, that every 6 seconds, it is producing a new block. So that's the L1 block time in our DevNet, like the local DevNet. And you can see it like every 6 seconds, it tells you something about an updated payload. And yeah, that's the L1 progressing. It's driven by the beacon node here. And then we can also go into the layer 2. So that's the layer 2 Geth client. And here you see that it actually is operating at a 2-second block time, right? 1, 2, 1, 2. And yeah, so this is basically the local chain progressing. And very interesting here is OP node, right? So this is then here the sequencer client that is on the one hand sequencing, but then on the other hand, it is also importing the batches that the batcher itself posted to L1. So you can find here, for example, messages like found next batch, and then it is importing the data from L1. Then you can also here see the batcher, and then you can see here, so it added 1, 2, 3, 4, 5, 6, 7 blocks to the channel. So a channel is just a container for blocks, and then it submits, publishes a transaction, and then successfully published. And then soon it will say something about the transaction being fully confirmed. Transaction confirmed, like you can find these messages here about transactions being confirmed, and then they will be imported on the OP nodes. And yeah, like this is how you can, you can try out anything and then just run it and then investigate the logs here. And also this is running on your local machine, so you can actually access the nodes, right? So for example, yeah, you can just use cast and yeah, then just check out the local chain. So 9545 is the port where the L2 will be running, and 8545 would be the port where the L1 is running. You can also see it in the block numbers, right? So 27 because L1 is slower, and 74 because L2 is faster. But you can also see that, for example, if you query the timestamp data from L2, you will see that that's the current timestamp in UDC. Because yeah, both chains are just progressing fine right now. And you have a fully Ethereum RPC client running here for L1, L2. You can interact with them. You can spin up additional nodes, right? So you could, for example, start that network and then try out something on a local fork, and then start another OP node, for example, and then see how this interacts with this network. That is guaranteed to work. Yeah. So the way you can configure the network is there's something called the DevNet L1 template. So this is a file just here. It's in the notes. I can also share later the notes. And here you can basically set up everything that needs to be set up for deploying a new DevNet locally. It's a lot of fields. Some of them need to be set, others not. We also have docs. So the docs website will also explain how to set this up. And then you also have, this is quite interesting. For example, if you want to understand, okay, how are the services actually defined that are running here, and on what ports can you access them? And this is then basically what you can see here. Okay, so next up, I want to talk about some abstractions and hack ideas. So there's the specs that describe, for example, how you can implement an alternative data availability layer. So the known ones are Ethereum data availability or blobs, but you can also have other data availability service. So for example, we provide a definition of a DA server. You can also think about it as a sidecar. And then, yeah, you can implement a DA server. For example, here in that file, you see how it actually defines an HTTP REST API to post and get data. So basically then the batcher would send the blobs or the blocks to that server and retrieve, and the OP node would retrieve them from that server. And then you can implement anything, right? So for example, this one here, the DA server already has an abstraction of a key value store. And then we have, for example, 2 implementations that use S3 and also file, right? So there's a DA server implementation here that uses S3, and then you see an S3 store implementation of get and put. And then, yeah, it's very, very lightweight, accesses the S3 for the data buckets. And this is how you could do your own data availability. Another thing is, for example, but this is quite hard, is shared batching and sequencing. Yeah, many things you can do there. So one example is if you want to understand how actually the data source is validated for the batches, you can go into this data sources file and then see how the data is ingested from L1 and how the verifications are done. Then you could think about, for example, changing the rules there to allow for multiple batches or something like that. You can also hack the execution layer, as we do. For example, we recently added with Fjord ROP 7212 support, which is a signature verification of this curve. And yeah, I just linked like one PR here that shows how you can add, for example, a new precompile to the execution layer. And then finally, you can also add new L2 assets like ERC 1155. That's just one example because we actually don't have a bridge for that yet, as far as I know. Yeah, you can actually see it here. So there's like a universal contract that defines how a bridge works. And then you also have like always an L1 and L2 counterpart. So you see it in the pact in the contract bedrocks. You see like L1, L2, and universal. This is like a common pattern you will see. And then the universal defines the common code, and then the L1 and L2 are just the adapters on the L1 and L2, how to build a bridge. But obviously, we don't really have time to go into the implementations, unfortunately. Yeah, and these are just a couple of ideas what you could do with that. And here are also some of the references I mentioned, and then there's also public Discord. And yeah, I think we're out of time, and that's it. And I would love to get some questions.
Sweet. Thanks, Sebastian. I believe there are a few questions on the chat box, so in case you want to go through that, that would be
Yeah.
great.
Yeah, let me just find that. Oh, yeah.
In the meantime, if I can jump in with a quick question.
Yeah, sure.
So if say I want to deploy an OP stack with custom precompiles, I saw that you mentioned you have a L1 and the L2 counterparts. Does it mean I need to have my precompile get approved? Say, for example, I'm building an OP stack that settles on optimism. So an L3, really. The L1 side of my precompile, does it need to be merged into optimism client for my L2 counterpart to be functional? I'm not sure if that makes sense.
Yeah, so what was a bit confusing, so there's one thing about precompiles and another one about bridged assets, right? So these are two separate things. So precompile is just like it's a contract that is available in the execution layer client directly for interacting with it. So this would be a
right. Sorry, I mixed them together. Okay, so then rephrase my just take back my question, but with the bridge asset. So say I want to make a custom bridge.
Yeah.
I need to make an L2 implementation, but then for the L1 implementation, how do I get that into the L1's execution client?
So on L1, it would just be a contract, right? So it would really be if you, I mean, especially in the scope of this hack, right? We are really thinking about a completely new L1 and L2 testnet chain, right? So not about mainnet or anything. So on your local L1 chain, you would then deploy a new bridge contract on the L1, and then you would also deploy an L2 bridge contract. Then they would be both linked together because they reference each other's addresses. And then via the mechanism of the Optimism portal, then you could basically bridge then assets via these contracts. And
got it. Thanks.
Yeah.
So the L1 implementation is just watching what's happening on the contract.
Yeah. So you have a contract on L1, and then you still use the underlying core deposit mechanism, and then that would interact with the L2 contract. Okay. Custom assets on top of 721. Yeah, totally. I mean, just anything that makes sense, right? Anything that sounds fun, I think you could do. L3 rollup. There's a question about L3. I can say something. Yeah, I mean, in general, you can do L3s, right? I didn't mention that, but that's something else you could try out in L3 or even in L4. There's just one limitation right now, which is a bit unfortunate because we have a very tight coupling between the L1 and L2 blocks. If you do an L3, you have to use a block time of 1 second. If your L2 has a block time of 2 seconds, because it needs some buffer to catch up. So if you use an so you basically couldn't do an L4 right now. So if you really wanted to do an L4, you would actually have to do an L2 with, say, 3 seconds, then an L3 with 2 seconds, so you can have an L4 with 1 second. Yeah, just that as a hint if you are diving into LNs. Delay finality. Yeah, so in general, yeah, there's a delay for withdrawals, and that's part of the protocol. It needs to be in order to be secure because you need this challenge window. But there are also there's additional liquidity providers that you can use. So basically, they take a little fee, and then you can instantly withdraw on L1 by using their service. So this is also something. Yeah, I mean, I don't remember the names of some of them, but there are services like this as well. Idea based on OP-Sec chains, publish assets. Yeah, I mean, for example, this is something you could do in the execution layer, right? You could say, okay, I think about a presentation, I think about a mechanism by which you allow transactions that don't pay ether gas, but some other mechanism. And then you could do that by introducing that into the execution layer. That's one option how you could do that, depending on how you want to pay for it. We also have very recently introduced something that we call custom gas tokens. So that means you have on the layer 1, you have an ERC20, then you can use that as a gas token, and then it would behave like native ETH on the layer 2. So this is also custom gas token, it's called, and you can also use that or build on that. So the DA layer, where it is fitting, yeah. So basically, actually, just going back to the here. So the DA layer would then replace this pink one here, right? So basically, instead of using the Ethereum layer 1 for data availability, you use Amazon S3 or whatever. The batcher would still propose commitments to the L1, right? So, but it wouldn't propose wouldn't send the full data. So it only sends let's say every hour, it would send a commitment to the layer 1 that is, for example, the hash of all the data that has been put into an S3 bucket. And then this is what would then trigger the other nodes because they still observe the L1 to then get this commitment from the data layer that you defined. So this is how you can do alt-DA. Risat, yeah, I mean, you can totally do that, right? You could build a mechanism by which you actually have, so you could filter people that you allow to transact based on, for example, some L1 contract. So actually, this is something I didn't talk about. So a standard mechanism for getting any data from L1 into the L2 is that we parse events, right? So logs or events, they're being parsed by the OP node, which is why the OP node also has to ingest all the blocks. So it's basically scanning each block for logs. And for example, we have something called the system config. And if we do configuration changes on the L1, then those changes are detected by log messages that the contract emits. And then you could think about also using a similar mechanism by having a special L1 contract that emits some event that allows people to transact on the network, and then you could restrict that by this. Yeah, so this is totally something you could do with that. Okay. I think we're 6 minutes over. Calvin, how's it looking?
Yeah. Yeah, I think we are definitely over time, but really good set of questions coming in from the attendees. I think this was one of the most interactive sessions I've seen in a while. So yeah, thank you, Sebastian, for taking your time and making the presentation. I really hope it was informative for anyone who's joined here from different parts of the world. Feel free to reach out to Sebastian or anyone from their team on Discord partner channel if you have any questions during the course of the hackathon, and they shall definitely get back to you whenever they're free. So good luck, everyone, and see you all soon. Cheers. Thanks, Sebastian.
And thanks everyone for listening.